So this is a question in which you have to perform Bayesian inference. Imagine a coin with outcomes heads and tails, and we denote yi as the outcome of the ith throw, and we'll take a value of 1 for heads and 0 for tails. And the important parameter we are looking at is pi, which is the probability to have a head. Now, our old friend Vlad is a bit of a sly character. He has indeed a normal coin in which the probability is 50%, but he also has two biased coins in which the probabilities will be 25 or 75% to find a head. So he comes and throws his coin 4 times, and we have therefore 4 outcomes, and they are 1, 1, 1, and 0, or 3 ones and then a 0. And we are now interested in which coin he brought, the fair one or the biased ones. We have a prior distribution, but what we are after is the posterior distribution. So we have a prior view, but we want to know how do we update this prior view given the 4 outcomes we have seen. And the posterior is the probability that of pi conditional on y, and that's proportional to probability of y conditional on pi, that's the likelihood, times probability of pi, which is the prior distribution. So we are after the posterior distribution. The prior distribution is given here. We're really only considering 3 values for pi to simplify the world. So we have 3 possible values: 0.25, 0.5, which is the fair coin, and 0.75. So we are dealing with a discrete distribution here, and it's that feature of the data that will make it easy to go through the calculations. If we are dealing with continuous distributions, then the calculations become less straightforward, although the idea will remain. So what about the likelihood? Now, if we have a head as an outcome, yi is equal to 1, then the probability to get that outcome given a certain value of pi is just pi. The probability of getting a 0 is 1 minus pi. So in general, we can write that down for both outcomes. We can say the probability for yi given pi is pi times yi plus 1 minus pi times 1 minus yi. That's just the 2 possible outcomes here combined. That's this outcome, and if the outcome yi is 0, then that is the probability. So depending on the outcome of yi, one of these 2 summed terms will be relevant. So basically we now have all the information we need, and what we now want to do is we want to do the updating to see how we adjust our prior distribution. Let's think about a tabular setup. We're having 3 possible values for pi: 0.25 and 0.5 and 0.75. So then our initial distribution, that's our prior, before we see any observations, is this prior distribution. What we next need is the probability for our outcomes given particular values of pi. And what we need to get our posterior is we multiply that with the prior distribution. Okay, so the likelihood times the prior. So that's what we're going to write into the next row of our table. And we use the information from our first throw of the coin. So our first information is we have a heads, so yi is equal 1. So the probability of getting that is 0.25 when pi is equal to 0.25, and the prior for 0.25 is 0.1. So the prior for 0.5 is 0.8, and the probability of getting a head with that is 0.5, and the probability of a head when pi is 0.75 is 0.75, and the prior of that value is 0.1. So for each possible value of pi, we combined our likelihood with the prior. And then we get values calculated here. And now it will be useful to use another column where we sum up all these values. As it turns out, all these values are 0.5 summed up together. Now clearly that's not a distribution. These values are just proportional to the posterior, so we need to scale these values up such that they sum to 1. So that's easy. We multiply them by 2 because the sum is 0.5. And these are the values we get. And this is now the posterior distribution after one throw of the dice. Okay, and we can think about this will turn into the prior distribution for the second throw. So let's update using the second throw. Again, it's a head, so yi is equal to 1. So we want to calculate the product of the likelihood times the prior after the first throw. So it's 0.25 times 0.05, 0.5 times 0.8, and 0.75 times 0.15. So the first, the black values, are always the likelihoods. The second are the priors. Now, let me do this in an Excel table, because then we can easily adjust it to reflect the extra throws. So let me first just replicate what we did for the updating after the first value. So we need the likelihood times the prior, but now I will write this formula such that it is correct regardless of whether we have a y outcome of 1 or 0. So I'll write both parts of the likelihood function here. And I just link that to the pi values in row 1. So you can try and replicate this spreadsheet, but if you understood what we did on the previous sheet, you can get all the right results as well. So we need to multiply this result with the prior value. But something isn't quite right. We have to put that multiplication, we have the first part, we have to put that in parentheses. So the first two summands are the likelihood, generic terms, then times the prior. So now once we've written the generic formula, we can just copy the formula, then we calculate the sum. That should be 0.5, that's good. And then we need to scale this thing, so we just divide by 0.5, which is the same as multiplying by 2. And we do that for all the values, and that ensures that our new probability sum to 1. So that was the posterior after the first throw, and that's exactly the same as the one which we calculated by hand. 5%, 80%, and 15%. And now we just copy this down. And of course, whenever you do that in Excel, you should convince yourself that the copied formulas still do the right thing. So they calculate the likelihood, that's the first two summands, and then multiply with the prior from the previous round, and that works for all probabilities. That's fine. So what we get here at the very end, this is now our posterior distribution after seeing all the 4 throws, 3 heads and 1 tails. So you could of course do these calculations by hand as well, continue doing these by hand, and you should get exactly the same result as in the Excel table. So it's just below 2% is now our posterior distribution for a coin with head probability of 25%, 81% that the head probability is 50%, and about 18% that the head probability is 75%. So our prior distribution after updating with 4 pieces of information has changed. It has moved probability from a head probability of 25% towards a head probability of 75%. So this is formally the posterior distribution of pi after seeing our 4 outcomes y1 to y4. So the second part of the question, as a frequentist, how would we go about obtaining information for our estimator pi? So if we are frequentist, we treat pi as unknown but a fixed value. And the question is, given our sample, what is our best estimator of pi? And it is really just the sample proportion of successes, which in our case is 0.75, so 75%. If you're a frequentist, you will regard pi hat as a random variable, but not the unknown pi, but pi hat is a random variable. It has an expected value of pi if your sampling is all right. It also will have a variance, and you may remember from your first year stats course what the variance is. That is pi times 1 minus pi divided by n. Of course, we don't know pi, so we use the estimated value for pi hat. If we wanted to perform inference, we needed to know how that random variable pi hat is distributed. Now, for large n, it would be distributed approximately normally. And then performing inference on a normally distributed random variable would be pretty straightforward. So then you could test hypotheses. For instance, is pi hat larger than 0.5 if you wanted to do that. But we're not going to do that here. So let's return to the problem part A. And what I now ask you to do is to rework the same problem, but rather than updating after every throw, I want you to think about updating in one go. So you see here when we went through this table, we updated 4 times for each observation we got, for each throw of the coin we got, we updated. And that drove how we calculated the likelihood part. However, what I now want you to do is I want you to adjust that likelihood part to not be the likelihood of y1 given pi and then y2 given pi, but to be the likelihood that you see y1, y2, y3 and y4 given pi. Now, basically what we've undertaken here is a binomial experiment. And in this binomial experiment, we have 3 successes in 4 throws. And of course, you know how to calculate the probability in a binomial experiment for 3 successes. Let's call them x. If you have 4 throws, let's call them n. Okay, so that's the probability. So we know the generic formula for px given n and pi is nx, or binomial formula, pi to the x times 1 minus pi to n minus x. So you'll have to think back of your year 1 stats to figure that out. So if we plug in our numbers, what we get is 4 times pi to the 3 times 1 minus pi. So that is our likelihood to get 3 successes out of 4 throws. So now we create our table again. It will be much shorter now. We'll only have 1 updating process. So here are our 3 possible outcomes, and our prior distribution is here. And what we now want to calculate is the likelihood given 3 successes, the likelihood for 3 successes in 4 throws given pi times the prior. So now if pi is 0.25, we plug that into that formula, then we get 4 times 0.25 to the 3 times 0.75, and that is 0.0469. Then multiplied with the prior of 0.1 for pi equals 0.25, we get that value, 0.00469. Then we do the same for pi equals 0.5. We plug 0.5 into our likelihood formula. We get 0.25 multiplied with the prior, which is 0.8, means we get 0.2. And then we do the same for pi equals 0.75. And here as our value, the likelihood is 42% approximately times the prior 0.1. We get 0.04219. So we calculate the sum. That is clearly smaller than 1. In fact, it's about this one, about a quarter. And then we have to rescale this for this to become the posterior distribution. Right, so once we rescale that, it will be the posterior for pi given all observations y1 to y4. So it will be approximately 4 times each of these values. Here we go. Okay, and that is, if you compare to part A, this is of course exactly the same result as what we got in part A. So it means there's really no need for the stepwise updating. That was just sort of a nice little tool to think about Bayesian updating, but you can do the updating in one step if you know the likelihood function for, in this case, 3 successes out of 4 throws.